Hey everyone. Today, I'm going to go through an example of how to do a Turing reduction. I'm going to assume a couple things of the kind of like where we should start, but um, this is an example of how you would go upon doing a Turing reduction that kind of proves an undecidable language. So the language that it also involves constructing a machine. So that's something that we've kind of gone through in homework. It can be a little confusing for students. So I wanted to try to clarify as much as I can. So the language that we're dealing with today is a language of finite. So that's what I called it. And what it says is it takes in a machine. Notice how this is the encoding of it. That's what the angled brackets means. That's we encode the machine. So we take in a machine and we say, hey, M is a Turing machine and its respective language is finite. So let's go through some examples. Some examples of this language could be they only take in numbers between 0 and 5 and they have to be discrete. So only accepts discrete numbers of between, let's say, 0 and 5. So in other words, 0, 1, 2, 3, 4, 5. It only accepts six numbers, which is 6 is finite. Therefore, this machine that decides this language would be accepted in the language of finite. So likewise, if you had a machine that only accepted, we'll say EEX 376. Can't spell 376. I can't spell EEX. That would also be accepted in the language because that machine, that language is finite. One thing that wouldn't be accepted would be the language of odd numbers. Why? Because the things that it accepts is 1, 3, 5, 7, etc., which is infinite. And therefore, it's not finite. Because it's not finite, it won't be accepted. So those are some examples of what kind of, some examples that what would be a part of this language and what wouldn't be part of this language. And now, what I want to talk about before we even get to the Turing reduction part is intuitively, what do you think this language would be? I already mentioned previously that it's going to be, excuse me, that it's going to be undecidable. But why? Why would something referring to the behavior of a language be undecidable? And what I want you to think about for this is, let's say you yourself was given a machine. Only thing you can do with that machine is you can't modify it. Only thing that you can do is put an input and send and get output. Okay, you can't modify the machine. How would you, as a person, aside from creating an algorithm, whatever, how would you test the language of this machine? What would you do? And in this case, if you wanted to figure out the language of a machine, you have to give it all possible inputs. You give it all possible inputs and see what happens. And you give it all possible inputs, it's going to loop forever. It's going to loop forever, especially if not loop forever. You have to go through all possible inputs, which will be infinite time. You have to go through every single possible one. And especially, what if you had a machine, for example, that just said, given any input W, you just said loop. Now it's really going to loop forever. So you can see that in these two cases that it's likely that this this language is undecidable. So what we want to do is construct a Turing reduction. Now, as we learned in lecture, if this next part is unfamiliar to you, so if this next part is unfamiliar to you, please go back in lecture and kind of rewatch this part. This part is the part I'm gonna mostly assume for the most part, just because it'll take this video become a lot longer if I didn't. But so we want to construct a Turing reduction. A is Turing reducible to B, and we want to prove that L finite is undecidable. So what we're going to do is I'll place it on the right side, place it in place for B. So we're going to say L finite is here, because we know that if we can prove that some undecidable language is Turing reducible to L finite, then we know that L finite is going to be undecidable, because just by the property of our Turing reduction. So what I like to use the most, you can use whatever you want. You can use LHalt, LAccept, or whichever one that we proved in lecture, unless specified otherwise in the problem. I like to use LHalt for these ones just because I'm most familiar with LHalt, but that's what we're going to do. So remember the first two parts of Turing reduction. The first thing that we do is we assume a black box decider for L finite, the B, our language on the right side. We're going to call this one F. And then two, we're going to create a decider for A. That's our two main steps of a Turing reduction, our two main steps. Create a Turing reduction for A, which also means, for LHalt. In that case, it was A. So created a decider for L Hall, so we're going to call this H. Now, this is what we have. We have H. H takes in two inputs. It takes in a machine and X. And now what we want to do is construct a decider for H, basically construct H using F. And now this is the part where most students get kind of caught up on, and this part that I want to emphasize the most. What I suggest as a method of approaching these problems is not to focus on constructing the machine first, like the whole decider. I suggest constructing the correctness proof first. Because once you construct the correctness proof, it gives you a plan of how to actually construct the machine, construct the decider. So here's what I mean. We know first and foremost that F takes in one input. F takes in a machine and accepts if that language of machine is finite, and rejects if language of machine is infinite. Now remember that F is a black box decider, so we don't know how it works. We just know that it works. It'll never, ever, ever loop. So that's the best part. It'll never, ever loop. Now, we also know that H takes in two inputs, M and X. It should accept if M halts on X and rejects if M loops on X. So these are the two machines that we have. We have F, which is our black box decider. And we also have H, which is what we're trying to create. Okay. So remember that the whole point of the idea is we want to figure out, does M halt on X? That's the main goal. That's all we really care about. And we're going to try to use F to help us figure that out. So what we want to do is construct relationships. Okay. What I suggest as the first step is construct a relationship between F and H. Because remember how in the end, in our lecture, we always have, we construct some sort of machine, whatever that is, and then we use our decider. We're going to call this machine M prime. We use our decider. We say run F on M prime, and then we have some sort of relationship between F and H, such as if F accepts, H accepts. And then if F rejects, H rejects. Oh, that's A. Now, this is the kind of the general idea of how our Turing reductions have gone. And notice how we create a relationship here between F and H, such that if F accepts, H accepts. If F rejects, H rejects. Now, you can create your relationship however you want. It could be inverse, for example. So if you wanted to do, instead, if you wanted to do if F accepts, H rejects, that's okay. And then say if F rejects, H accepts, that's perfectly fine. If yes, then no. If no, then yes. That's okay. You can construct your relationship however you want. You can do if yes, yes, or if accept, accept, if no, no, or you can do the opposite. If yes, no, if no, yes. You can do it however you want. What I like to do is just make it simple at first and say if yes, yes, if no, no. And if there's a problem that occurs in the future, I will switch it as I need. Okay. So what I'm going to do is construct that relationship and say if F accepts, actually, I'll say it right here. So we say F accepts something. We'll say M prime. So we're going to pass an M prime at some point. We want H to accept M and X. And if F rejects M prime, that means that H should reject M and X. Now, again, that's how we constructed it. We just want to create a way for us to, well, given the results of F, that we have a result for H. That's what we're trying to do this entire thing, right? We're trying to use F to help us create H. So the first thing we want to do is construct a way that whatever the input of F is, we know what H should do as a result. Now, again, this is more counterintuitive because this is usually the end of your correctness proof. But what I'm proposing, what I'm suggesting is focus on this part first, because this will help you give way to what you need to do to construct your machine. So now we know that if F accepts M prime, H should accept M and X, okay? And if F rejects M prime, H should reject M and X. Now, when should H accept M and X? Well, H should accept, let me move this a little bit. H should accept M and X only if M halts on X. So we say if, we actually don't even need the if here. So we say M halts on X, something, question mark here. This leads to M prime, which means H accepted. This leads to F accepting M prime, which means H accepted M and X. And likewise, if M loops on X, some question mark here, what we're going to do, F should reject M prime, excuse me, and H should reject M and X. So now again, we're still constructing this relationship. If M halts on X, we know for a fact that H should accept it. And the way we construct our relationship, that means F should accept M prime. So in this case right here, in this case, we need to construct, in the case that M halts on X, we need to construct M prime such that F accepts it. We need to construct M prime such that F would accept it in the case that M halts on X. Well, in what case would F accept M prime? Well, let's go back to here for a second. M accepts M prime if its respective language, oh, my Apple Pencil just died. That's unfortunate. Yeah, 1 second. F accepts M prime if and only if the language that it decides is finite. So if it only accepts a finite number of inputs and rejects if it's infinite. So what if we just, in the case that M halts on X, what if we just forced our machine to only accept a finite number of inputs? Let's try that. So we say in our machine, takes in any input, right? Run M on X. Okay, run M on X. If it halts, how we want to enforce a finite set of inputs. What we can do is just reject everything. If we reject everything, why? What would that do? Well, if we reject everything, we accept nothing, which means the language of our machine is the empty set, which is finite. So again, you can do whatever you want for this. You could say if W is equal to 1, accept, else reject. And that forces our machine to only accept the number 1, which is, again, it's just one element, so it's finite. You could say, oh, if it's 1 and 2, or 1 or 2, then accept, otherwise reject. You have your language to be 2 elements instead of 1 this time, or 0. Whatever the case, you just want to make sure that the language is finite. So I'm just going to choose to reject everything because that's, for me, is the easiest. So I say, if it halts, reject. If it halts, reject. Now, we constructed this part of the machine. We have to consider the case where M does not halt on X. Now, the thing is, what you might be tempted to do is you might say, hey, else do something else. Do some action. The problem is, if M indeed loops on X, we will never get past this line. Think about it in C++. If we had a while true, and then bam, 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 we would never leave the statement. We would never get out of the while loop. Same thing. If we're looping on X, we'll never leave this line of code. We'll never even get to the halt statement or to this statement. So we need to make sure that whenever we loop on X, it still fulfills this relationship that we are trying to construct. This relationship right here. So remember, let's go back to what we were doing. And let's say, hey, we said run M on X. If it halts, reject everything. Why? Because we said, if M halts on X, we want the language of M to be finite. Why do we want that? Because then F would accept M prime, and therefore H would accept M and X, which is what we want. So that works for this line. Well, let's check looping for a second. Now, if M loops on X, what's his language? Does it accept anything? No. If M loops on X, again, please don't do this. This is the wrong thing. You're not supposed to do that. If M loops on X, that means it does not accept anything. So if M loops on X, it accepts nothing. And therefore, the language of the machine is also in the empty set. I don't know if that's correct notation. I would say it just is empty. Cool. This is somewhat problematic. Why? Because we wanted, in the case that it loops, we wanted F to reject M prime. And how do we reject M prime? The language of M prime, here you go, let me put that M prime here, sorry, is infinite. But in the case of looping, we can't do anything because it's going to, no matter what, be finite because it won't accept anything. So this is the case where I talked about how where you initially construct your relationship between F and H. You choose either accept, or you do accept, reject. You can choose yes, yes, no, no, or you can do yes, no, no, yes. What you construct as your initial relationship, you have to make sure you test it in the end. Because we see in this case that if M loops on X, it automatically is a finite set, automatically, because it will accept nothing. So we should probably inverse our relationship. So instead of having our M prime be finite in the case that it halts, we want that to be in the case that it loops, because we know for a fact that no matter what, it's going to be finite in the case that it loops. So let's make this relationship, let's make that finite. And we make this one infinite. Okay, and so then we'll change this. We'll say, hey, if F rejects M prime, we want H to accept it, because remember, it's going to be infinite, so it should reject. And then over here, because it's going to be finite, we want F to accept. So notice how we changed our relationship in the end, because we wanted to accommodate to the fact that looping produced a finite set all the time. We cannot change that idea because it's stuck. So we have to accommodate. So we change our relationship to adapt to this idea. Put an arrow right here. So we know that looping is going to produce a finite set. We want, in the case that M halts on X, right here, in the case that M halts on X, we want the language of M prime to be infinite. How can we do that? Well, how can we make sure that it has an infinite set? Well, let's just have it accept everything. You can do literally whatever you want for any infinite set. You can do the language of odd numbers is infinite, right? So you can say accept only if W is an odd number, which is an infinite set. You could say literally whatever you want to make sure that it's infinite. I just think it's really simple to say accept everything. We know for a fact it's going to be an infinite set. So in the case that it halts, accept. Now let's test it. If M halts, if we run M on X first, if it halts, we accept everything. Does that work? Okay, we say M halts on X. We want the language of M prime to be infinite, which is true because it accepts everything. And therefore, F will reject M prime. And therefore, we have H accept. And in the case that it loops on everything, if M loops on X, that means it accepts nothing, which means that the empty set is, the language of M prime is going to be finite because it's empty, which means that F should accept M prime. Therefore, H should reject. So we constructed a machine such that it fulfilled our correctness proof. Now, this is the part I really want to hone into, because most people will try to construct a machine first and then hope that it works. What I'm suggesting that you do is construct the correctness proof first. Construct the correctness proof first, because then it'll guide you to how you want to construct your machine. Because you want to construct your machine M prime such that it helps you fulfill this relationship. It helps you lead to the answer. So that's what we did. We wanted to, in the case that M halts on X, we wanted our H to accept, and therefore we wanted our F to reject. And the only way you can reject M prime is if it's an infinite, if the language is infinite. So we made sure that it's infinite. And in the case that M loops on X, we wanted H to reject. Therefore, we wanted F to accept M prime, because of the way that our looping worked is always going to produce a finite set. So we wanted to make sure that M prime only has a finite number of inputs that it accepts. And we did, just by the very nature of looping, that it accepts nothing. So we constructed our M prime such that it fulfilled our relationship. Oh, it's almost dying. No, don't die. Please don't die. Okay. My iPad just almost died. Oh my gosh. Okay, so let's finish our proof. We say run f on M prime if f accepts, reject, else accept. And that's it. We constructed our, let me move this for a second. We constructed our machine such that we used f to help us figure out whether M halted on X. And we first did that by constructing our machine, by constructing our relationship, and that helped us figure out how to construct our decider. And I'm going to do this in terms of how you should write your correctness proof. And again, you've been ideating your correctness proof the entire time, but for sake of formality, what you want to do at each end of your Turing reduction is say, let me group this, turn this on for a second. You say, go through every possible case. So we say, if M halts on X, yeah, actually, I don't need the if. You say, what happens when M halts on X? Well, M prime accepts everything. Everything. Which means that the language of M prime is infinite. Which means that F rejects M prime. And by the very nature of our thing, if F rejects, we accept. So H accepts M prime, or M and X. So likewise, if M loops on X, M prime accepts nothing just by the very nature of looping, which means its language is finite. F will accept M prime as a result. H, therefore, will reject by how we construct our relationship. And then the last thing you want to write is because H halts on all inputs, it's a decider. Because H halts on inputs and correctly decides L halts, it's a decider. So that's it. That's how we constructed our Turing reduction for proving that L halt is Turing reducible to L finite. And again, going back to the original question of, is this an undecidable language? You can think about it in two ways now. We proved first and foremost that L halts is Turing reducible to L finite. So because you prove this relationship, we know that L halt is undecidable. And by the properties of Turing reductions, you now know that L finite is undecidable. You can also think about it as a proof by contradiction, in that because we created a decider for L halt, that's a contradiction because we know for a fact that it's undecidable. So we can't say that we have a decider for L finite. So therefore, if there's no decider for L finite, excuse me, there's it's undecidable since there's no decider. So that's the entire thing. And we can say now, thus L finite is undecidable by proof by contradiction or by Turing reduction properties. Either one. So that's that. Again, what I really want to emphasize for this is the fact that we started off writing our correctness proof. The first thing that we did was we constructed a relationship between F and H. Because remember, we want to use F to help us create H. So we first construct our relationship. You don't know what you're going to pass into F at this point. but we just wanted to establish something, some sort of guide that can help us. So we said, if F, we initially did if F accepts, H accepts, if F rejects, H rejects, but then we realized we had to modify that in the end. So then we inversed it. So we said, if F rejects, H will accept. If F accepts, H will reject. Yeah, I don't know if I messed up the wording of that, but you can see it on the screen. Like then we realized that given this relationship, we have to have some sort of property for halting. So in the case that H accepts, M has to halt on X. So we know that. Then in order to fulfill that relationship, we had to construct a machine that could fulfill it. In the case that M halts on X, we wanted F to reject. So we wanted to force our machine M prime to have an infinite language. We wanted that. So we enforced that by accepting everything. And in the case that M looped on X, we wanted to have F accept our M prime. So we also enforce that by saying it accepts nothing, which means it's finite. And again, we didn't say if it loops accept nothing. We just, by the very nature of looping, it accepts nothing. So that's just our correctness proof right there. Again, when you're doing this, you have to look at the looping aspect of it and what happens when it loops, and make sure that it fulfills your correctness proof relationship that you were creating. If it doesn't, you have to modify something. And yeah, I'm trying to think of anything else I want to mention. Oh, in terms of creating a machine, there's a couple ways of, I know the idea of creating a machine is a little unintuitive at some points, that I kind of skipped over that part because we talked about it in lecture and in discussion. And this video is already getting long enough. But the idea is F only gets one input and H gets two inputs, and we can't pass in M on X into F because it only accepts one input. So we have to do something to sort of mimic that behavior. And notice how we hard coded M on X in our machine. And simulated the input, and that's basically what we did. We allowed F to get the results of M on X instead of running it itself, or we basically hard coded the results of M on X and passed that in rather than just passing the two parameters itself. So I know that part's a little intuitive. I didn't go too much into that, but perhaps you already believe me that most times you're gonna have to construct a relationship for undecidable languages. So yeah, that is the main idea. So please remember, mess with the idea of constructing your correctness proof first. I think it would really help in terms of constructing your machine. If you're confused on the idea of why we constructed the machine in the first place, please post on Piazza. I think all of us are willing to help. So anything else for this? No, I think we are all set. Yeah, just really focus on doing the correctness proof first and then the machine, and then I think you should be set. Yeah, have a great day, everyone.